Professor Tobin Marks and also Mrs. Marks. Welcome. And also colleagues. And we also have colleagues from PolyU and also from Hong Kong U, okay, come here to listen to Professor Tobin Marks' talk. And also all the fellow students, welcome. You know, it's my great honor to introduce my longtime friend and also my mentor, okay, Professor Tobin Marks. And Professor Marks got his PhD degree, okay, from MIT. I think so your advisor, Cotton, right? Mm-hmm. Professor Cotton is also well-known inorganic chemist. So, you know, through the career, right, and Professor Marks almost actually obtained all the award he can receive, right? Okay, so you know, later on he is going to use one slide to also introduce his interdisciplinary research area, covers so many different areas, right? Okay, and a lot of people thought, you know, Professor Marks is very good in organic electronics, in the inorganic transparent conductors, but then he's actually the most well-known one is actually in the catalysis work also, right? Okay, so I just want to name few of the his achievement, okay, and also distinguished awards he received, right? He received also the highest scientific award in the United States, okay? This is a National Medal of Science, okay, in the United States, and also received the highest award in Material Research Society. That's a Von Hippel award, okay? And so he is a Academy member of U.S. National Academy of Engineering and also other different countries, right? But then also in the U.S., what is that? Okay, you know, Academy of
National Academy of Science.
Academy of Science also, right? Okay, and you know, just since you know, Professor Marks is a well-known chemist, right? Okay, he almost received all the awards from chemistry, from the ACS award in catalysis, ACS award in inorganic chemistry, ACS award in the chemistry of materials, and what else? Okay, I think they also have another one. Okay, I just only remember the few of those, right? So, but then, you know, he has published more than 1,200 papers, right? And you know, just astonishing is even with about 260 patents, okay, right? Okay, so you know, I can actually from industry, right? I was proud, you know, I also have many patents, but compared to Professor Marks' record, okay, it's going to be pale, you know, compared to your record. Okay, so you know, it's a wonderful opportunity to invite such a distinguished chemist, material scientist to come here to share all his wonderful work, okay, with us. And the title of his talk today will be How Do We Create and Process Materials for Flexible Transparent Electronic Circuitry, okay. Let me introduce Professor Tobin Marks.
I've been here about, what, 11 days now, 12 days? I will be here through February 8th, so if people want to drop by and speak to me. I'm right now located right next to chemistry headquarters, but I'm moving to IAS next week. So if you don't see me in chemistry headquarters, it's not because I left town. So what I wanted to do today, and I'm really honored to be a senior member of the IAS, and my classmate in the IAS in the chemistry is Jean-Marie Lane, who's a Nobel laureate. I saw him just a few weeks ago. He said, oh, you'll really enjoy it, and he was right. I'm really enjoying it. So this is the group as of about a year ago. It's very international. It's very interdisciplinary. They're physical chemists, organic chemists, applied physicists, a material scientist or two here. They're both theoreticians and experimentalists. And it's very common at Northwestern to have a student who will jointly work for two faculty members and be jointly precepted. And that, to me, is really exciting. And it prepares students for either research in the modern interdisciplinary fields, and those are all around us, or for industry or national laboratories. So it's interdisciplinary. We make things, because in my feeling, My feeling is if somehow, you have to rely on sigma Aldrich for every compound you're dealing with, something is lost, and something in terms of inventiveness and creativity. So we do a lot of different things. We have collaborations with companies, with national laboratories, and part of the whole thing is that people help other people. Themes in our group are shown here, and this morning we'll talk about unconventional electronics, how to use materials concepts to make very different kinds of electronics than you might make with silicon for very different kinds of applications. But on Monday, as a chemistry materials science joint lecture, I'll talk about catalysis. 30% of the world's GDP can be traced back to catalysis. If you know the Haber process to make ammonia, about 70% of all the nitrogen in your body came from the ammonia that was used to fertilize the plants. And so we'll talk about catalysis that day. So let's start the lecture today, and it sort of starts with a dream. And Alex has been involved in this area of science as well. The dream is there's one technology and only one on Earth that can make as many features per unit time as a silicon fab line. And that's a modern newspaper printing plant. And in that kind of technology, which we all know, the paper moves at hundreds of meters in just a few seconds. With modern graphics, you can print very, very elaborate kinds of patterns. For what we're going to talk about, you don't need to get to the 8 nanometer node, so we don't worry about that. But the other thing is every time Intel or Taiwan Semiconductor, whoever, wants to change a chip, that means billions of dollars and a lot of time. On the other hand, they print a new New York Times or London Times or whatever Hong Kong paper you read every day. So very rapid flexibility and reconfigurability. And so this is an example of a company in Germany. It's called roll-to-roll manufacture to print in integrated circuits. And what would you do with those? And why would you need such high throughput? And RFID tags, imagine when you go to the grocery store, rather than some poor person swiping everything over the bar code in one zap, it interrogates everything in your shopping basket because the RFID tag is printed on the product, and it could have within that tag information on storage, had it been exposed to high temperature, inventory information, price information, all connected to the store's computers and the warehouse's computer, et cetera, et cetera. So a very rapid way of acquiring that information. The other thing is if the particular consumer shopper might put something in their pocket or something, it will detect it and also charge them for it. So hope that doesn't disappoint anyone in the audience. Display backplanes. Imagine that you could print a Kindle by layer a printing process, and it would be flexible. See, this is part of roll-to-roll. E-books, sensors, smart packaging, displays, photovoltaics. We'll talk just a little bit about printed solar cells in a minute. And this whole idea of the Internet of Things, that there would be information acquired all over a city that would be relayed probably by Bluetooth or something like that to central parts, and it could be detecting a fire. And for example, if you think in a forest, if you had a little temperature sensor every few trees and then a little monitoring system, rather than somebody waiting till they see smoke, it would detect the temperature surge immediately. And lots of things, pollutants, poisons, all sorts of things. But to do that, and to do that on a huge scale, and the people who are pushing the Internet of Things say that the silicon industry can't make enough devices to satisfy that need. And to make them flexible, and so to do that, though, you're going to need new material science and new chemistry and new physics. You're going to need some very unconventional materials. So, for example, imagine that I want to print on plastic. I probably want plastic inks, i.e. organic inks. So I'm going to need N and P-type semiconductors for complementary organic circuits. We'll talk about that. They didn't exist. What about gate dielectrics? Well, we're going to need, again, printable gate dielectrics. And also, if you think about it, probably there'll be some elements of these circuits that are hard matter, inorganic, and some that'll be soft matter. What about synergy between them? How do we build that into their chemistry? So let's start for the students in particular about how a transistor works, a field effect transistor works. So it has 3 electrodes, a gate, a source, and a drain. There's a dielectric here to separate the source and the gate, and there's the semiconductor. And all this device does, you might look at it and say, gee, that's what's the big deal? It acts as a valve or a switch to allow current to go from this electrode to that one. And turning that on and off will be achieved using the gate dielectric. And that's all basically we need for all the modern logic circuitry that you have in your cell phone and probably your toothbrush this morning and all sorts of things. So if we put a bias between the source and the drain and none between the source and the gate, nothing happens. But that's good. That means, for example, we don't want leakage through the dielectric. But now if I put another bias, then I have what's essentially what the field effect is about. I create carriers in this channel right between the near this interface here, and this current will flow. And the kind of output I get then, an output plot would look here. Here's the voltage here and the current. And then you notice as I increase the gate voltage, I create more and more carriers. And the current flowing through that device is simply the density of carriers times their mobility, how easily they move. And that's all about chemistry and material science, how we achieve that. And you can plot the data another way. Here's gate voltage and current. And you get something called a transfer plot. And what you want in all these devices is this to be very steep. When it's off, it's really off. When it's on, it is really on. And you can plot it. So this is called the subthreshold swing. And you can plot it versus a different function and extract from this the threshold voltage. We want a moderate voltage to turn it on. And from this slope, I can extract the field effect mobility, so how mobile the carriers are. There's certain physical assumptions, and so the new materials, and we're going to talk about new materials today that never existed before, we have to worry about all of these parameters, the mobility, the on-off ratio. When it's off, it's going to be really off. You don't want it draining your battery. When it's on, it's going to be really on. The threshold voltage, how steep this is. And we'll talk about the dielectric. Now, you might look at the dielectric at first and say, boy, that's kind of a dumb material. It just sits there and doesn't do anything except insulates. We're going to see that there's some real challenges here. They were challenges for the big players like Intel as well. Now, let's look at, I won't hold my laptop up, but this is a liquid crystal display, Sony. And so behind the back plane for all of your laptops, if it's a liquid crystal display, is a set of transistors which turn on the little pixels on and off. And historically, they've been amorphous silicon. Why? You need to coat a big area. And the mobility is about 0.5, and the on-off ratio is about 1 million. It's only N-type, so you lose any advantage of having both N and P. And it's a poor current carrier. But it holds that voltage to turn the LCD mesogens and get the pixels to work. Now, if you go to an OLED display, you can't use this because it deteriorates when you're trying to carry current. And this, in fact, we'll see is being replaced by another inorganic. But this is the state of the art. You've got to be able to beat these kinds of parameters if you want to get somebody interested in your semiconductor. So let's now go over what I want to talk about today. We're going to talk about new organic semiconductors, or you can cross this out and say inks if you'd like, and their properties and their design. How do you design them? And then we're going to talk about the gate dielectric. And I'm going to show you how important this is for the devices and some designer gate dielectrics. Very, very thin, high dielectric constant. And then you might say, this guy he seems to be just an organic chemist. So nothing wrong with that. But the last topic is going to be oxides, amorphous oxides. And I'll show you some transistors, some hybrid devices, and some really unusual heterojunctions. So let's start with the organics. And the challenge was the following. When we got into this field, p-type organic semiconductors. So p-type, you can think of it as radical cations, or holes, moving through the highest occupied molecular orbitals of this material. So it turns out we're going to want pi systems. We're going to want pi systems that are in communication. And that, at least when we started, people knew something about that. N-type, meaning radical anion, when electrons move through the lowest unoccupied orbitals, the LUMOs, very little was known. In fact, there was theory that said, oh, those orbitals are too diffuse, they don't overlap well, you'll never get a good semiconductor from an N-type semiconductor from an organic. Give up, you're wasting your time. So that challenged people, including us. And here was our idea. First of all, we want to lower the energies of the LUMOs, because the lower the energies of those electrons, mobile electrons are, the less susceptible they'll be to air oxidation, atmospheric deterioration. And to do that, so the idea was we're going to have a pi system, and think of it, we're trying to make something like a stack of poker chips, and the electrons are going to move through that stack from pi system to pi system, and also, of course, within the pi system, and we're going to add electron withdrawing substituents to drop the energies of the LUMO. That'll make it very easy to inject the electrons from the electrodes, and substituents to make them soluble, a flat architecture so they'll stack, and rigid structures so this Marcus reorganization energy, when the electron hops from one molecule to the other, there won't be a huge reorganization barrier. And then if we really master this chemistry, we're going to link these together to make polymers. So I won't go through a whole bunch of chemistry, but let me show you just two examples of how sort of you can tweak and tune this chemistry. So we're going to take this basic core here. It's got thiophene groups and these tin groups. And then we're going to do a catalytic reaction that links this with this electron acceptor, this naphthalene diimide, to make a polymer. And we characterize these in all the ways that one characterizes the structure and molecular weight distribution of a polymer. And this is N-type because of this very powerful electron acceptor. If I do similar chemistry but add this electron-rich building block here, both of these are copolymers. I make a material that's p-type. And both of these have roughly the mobility of amorphous silicon. They're soluble. You put on organic groups that make them soluble. You can make two kinds of transistors. This is one where this is called a bottom gate, top contact, gold contacts. Bottom gate is silicon here. And this is a top gate, bottom contact structure. And we can make p-type transistors from this one and n-type transistors from this one. We can inkjet them, and this is a side view just showing the little droplets being inkjetted onto the contacts here. So this is this kind of structure here, architecture here, and we get a quite reasonable complementary inverter. So by having both n and p-type electronics, you get much higher operating frequencies and lower power consumption. So this is one, just mainly to illustrate how you can tune and tweak the properties. Here's another type. This is then N-type, very electron withdrawing groups. P-type, these thiophenes make it very electron rich. And we simply inkjet them over the contacts. And this is a very fancy, probably overly fancy materials printer we have for doing that, but you can program exactly how you want it printed. And again, you can make a very nice inverter. Inverter you can use for things as simple as AC to DC current change and things like that. One more N-type. This is work actually with the Imperial College Group in the UK. So they made this material here, and I mean, there's a couple of things that are interesting. These start to look like indigo dye molecules. And you could even imagine if you're making a solar cell, you can use nature-inspired materials. But what's amazing about it is it's very flat, and if you do the X-ray diffraction, you see that you can see in the diffraction not only the stacking, this order in the stacking this way, but from stack to stack you can see order, but even along the stack you can see the despacing from this to that to that. And so mobility is about 3, and the best that people have been done that, that is accepted as a reliable number is in this ballpark for an organic. And this is now about 8 times amorphous silicon. That's pretty interesting. And that's sort of how far we've pushed that. But if you really know for these organic molecules how to control the HOMO-LUMO spacing, which is the band gap of, you would say, a materials person would say the band gap, and the mobility, and you do little tricks like this. These weak non-bonded interactions help planarize the structure. Think of these as tapes then. We'll dope them with a fullerene or some other acceptor, and you can make solar cells. And so here's the front transparent window and the other electrode, and so holes are going to go this way, electrons this way when you turn on the light. The first thing that struck us when we made these and looked at the initial data was this kind of squareness looks like silicon or SIGs. Most organics are much less abrupt here, and it means it has to do with your ability to extract current at this voltage, and it's called the fill factor. And these were record fill factors for an organic transistor, for an organic solar cell. And now we're up with power conversion efficiencies on the order. I think the best we have of last week is about 12. So this field is advancing, and again it illustrates if you understand what makes the organic semiconductor work, you can manipulate it in really useful and interesting ways. Now let's go to dielectrics. This is the insulator. This prevents current from leaking between the source and the gate. So it's really, really important. And if I look here, let's just focus on this part of the transistor first. There's something really interesting. The physics says that the current between the source and the drain, we want to maximize that, of course. That's going to light up your OLED. Scales is the mobility. We talked about the mobility. The voltages, you don't want to have to run a cell phone at 100 volts, right? What kind of a battery are you going to need for that? So you want the voltage small. And so the other parameter we haven't talked about yet is the capacitance of the gate dielectric. And that's related to the dielectric constant of the material, and you want it as thin as possible. And in fact, Intel ran into real problems as they begin to scale down their transistors. You start getting leakage, and if you use silicon dioxide, you start getting leakage here through the dielectric. So instead, they switched to a hafnium compound, hafnium oxide compound, much higher dielectric constant. They could make the dielectric layer thinner. The problem is, for us, Intel processes at about 750, 800 C. We want to put these on plastic, and you can only imagine what's going to happen to a piece of plastic at 700 C. So we designed some materials, I'll show more in just a minute, which involve self-assembly of different layers. They're nanoscopically thin, they have high dielectric constants, very good insulating properties, and we call these self-assembled nanodielectrics. So I'll show you a little bit more about those in a minute. But the bottom line is, to our amazement, they work very well for almost every kind of transistor material you can imagine, and semiconductor you can imagine. And the reason is they suppress charge. Charge trapped in this part of the transistor gives you a hysteresis, which is really bad. I'll show you that in a minute. But just here's some examples of work we've done with John Rogers and some of his silicon nanomembranes. This is work with David Jaynes. So these are two card-carrying, device engineer types. We made an OLED display using sand as the dielectric. And we've also done radiation hardness testing of the sand materials. And this whole module went up on the International Space Station. We've done other tests with the Naval Research Lab. They're really quite robust. But also, it's a wonderful sort of exploration area to let your chemical intuition develop new kinds of materials. So these all have silicon layers. You have to do it under nitrogen. These use alternating metal oxide, and again, always an organic pi system, metal oxide. And Alex, you may remember this was originally an NLO chromophore. And these you can grow under air, and I'll show you some of the properties. Now, if you don't like solvent at all, these are two. We called this V-sand, and this has little ALD alumina cappings. These are very good if you want to avoid solvents. And you might say, boy, you might say you've drawn a cartoon. How do you know you really have something like that? So here's cross-sectional area TEM. This is just showing the self-assembly process. So it's Howard Katz, Bell Labs, zirconia layers, and then this stilbazolium type phosphonic acid group. So you build up layers. You usually build up 4 layers is enough. They're stable to 350 C. Really quite inert to most solvents. Here's the X-ray reflectivity. And so this is the 4-layer. And the data points, the fit is right on top of the data points. Here's 1 layer. So it's the diffraction. And of course, the zirconia or hafnia is doing most of the scattering. You can do the Fourier transform of the X-ray reflectivity, and you can see the different layers. So here's 4 layers. Here's 1. Leakage is small. The K for the hafnia material is roughly 20. So that's very, very large. And so these are solution processable. And let me give you 1 or 2 examples of why you might want a material like this. So this is a if you take single-wall carbon nanotubes, purified, sorted, semiconducting ones, and spin them into films and use silicon dioxide as the gate dielectric. And this is the transconductance, but think of it as the current, the gate voltage, huge hysteresis. And that's bad, except if you want a memory device. That's trapped charge between the semiconductor and the dielectric. On the other hand, if I use sand instead, look how crisp this turn on and turn off is. And the mobility is close to a record. Most of the world is sort of over here, and this one is somewhere over here. So very, very good gate dielectric materials. And we'll be seeing more of them in just a couple minutes. But this is a really time to step back and say, well, what is the algorithm for designing a molecule-based gate dielectric? Where do you start? You're just going to mix things together and see what happens? No, not at all. So my colleague Mark Ratner, who's a theorist, well known in Hong Kong, recruited a joint student, and Henry Heitzer, and the idea was, can one develop a computational quantum mechanical scheme to calculate the dielectric constant of these layers? And so it's one of those things, the professors will recognize this. You give a project to the student, he goes away for a few weeks and says, it won't work. Okay, we've all heard that, right? And you're sort of dismayed, but this kid says, but I did some more digging and I figured out how to make it work. Wow. So, and it works. And so this is just showing, so we said, well, start with a layer of benzene molecules. This isn't a sand dielectric yet, but calculate the dielectric constant. And so it's a plane wave periodic DFT calculation. And here's some organic molecules, for example, chloro and fluorobenzene, and you can actually calculate the dielectric constant profile along this direction. Now, you can vary the coverage of the molecules. You can push them closer together, pack them, and get these. And at this point, we said to Henry, well, is there a connection with reality here? And so he took the benzene crystal structure from the literature and computed the dielectric constant. This is the number he got, and this is the experimental number in the literature. So it's a very powerful tool for designing gate dielectrics. And just to give you some little bits and pieces, so here's, this is in a polyacetylene type structure, and here's polyethylene, and this is surface coverage and dielectric constant. And if you put on polarized, I'm sorry, we lost a bond somehow, got there which shouldn't be there. But if you take a polyacetylene and just put on large polarizable iodine atoms, you can get some really high computed dielectric constants. And so 12 is pretty good. Now, Colin Van Dyke came along, and he was a postdoc, and he said, what you really should be doing is take these molecules, and as you move them together, let the orbitals mix. And what you see here is really remarkable, and sort of plotted the way a physicist would plot it. Very, very bright guy, but the capacitance doesn't have to be. So here's the dielectric constant of a chain and of these kinds of molecules. And what you see, it's not linear. In fact, when you get the chain longer and then you pack them tighter and tighter and tighter till you get down to the van der Waals radius, it becomes nonlinear. And you get higher capacitances than you would normally expect. You can also do one other thing, and I'll do this and then I'll do that. This is something called quantum interference, and it turns out the people who make molecular transistors by putting a conjugated molecule between two electrons have noticed that certain structures, this an organic chemist would call cross-conjugation, and this is measuring basically the conductance versus the energy difference to the Fermi level. There are regions where all of a sudden the conductance falls to the floor. And this is called quantum interference. Now the problem is, if you were going to make gate dielectrics like this, is these are still modest dielectric constants. So what happens if you put donors and acceptors, a classical tactic strategy to increase the dielectric constant? And you can see you can get really quite sizable dielectric constants. We want to go higher, and you still get this point where the conductance falls off. So we think this is really interesting. Now, you might say, well, wait a minute, I got some inorganics that have high dielectric constants. The trouble with a lot of them is they're semiconductors. They have a high dielectric constant because the band gap is small. And so they're not good at insulation. All right, let's go to the last topic, and we're going to put it all together, because that's what fascinates me, is bringing together dissimilar kinds of materials. And we're going to talk about amorphous oxides. And let's start. I think most of the students have heard of ITO, right? Tin-doped indium oxide. It's on the window. It's probably on the window of the cell phone. So it's a transparent, optically transparent electrical conductor. And you sort of say, wait a minute, how can you do that? We'll say a little bit how you can do that, but these are things you can dream of, which are really extraordinary. Imagine flexible, transparent TV screens and displays. Imagine a decal that you could, an OLED decal, transparent, that you could put on your windscreen, and it would have all the GPS information. And it could be, addressed by Bluetooth or a thin wire. So all sorts of fascinating things. This is from the Sharp website. Sadly, Sharp does not exist anymore. But it's about IGZO, indium gallium zinc oxide. And we'll talk about that. But you can see here the motivation in a display is, if I have as I said, these displays, the LCD displays are turned on and off. The pixels are turned on and off by little transistors. The smaller you can make the transistor, meaning higher mobility, will allow you to make a smaller transistor. And if it's optically transparent, you get a huge amount of real estate. You can make much, much higher resolution displays. And if you get away from amorphous silicon to indium gallium zinc oxide, you got the current to light up an organic light emitting diode. We'll say more about that. But we asked, so IGZO, indium gallium zinc oxide, we asked, how would you hybridize it with organic materials, in particular thinking of OLEDs and thinking of all the organic electronics we talked about already. So let's first say something about how does a transparent conductor work? And this is a picture that goes back to John Goodenough, but other theorists, Alex Zunger, Julia Medvedeva, Art Freeman have pursued. So here's the idea. All of them are these heavy late transition metals. And if I make an oxide, let's say indium oxide, This is the energy, and this is the density of states. How many energy levels are packed? So the way the electron count works is the valence band is largely oxygen-centered. The conduction band, if I had indium oxide, so ignore this part here. If I had indium oxide, it's empty, but it's S states. So you say, well, what's so special about S states? Well, they're spherically symmetrical. If you bend them around in different ways, the spheres still touch, and you still have a band structure. If I take that indium oxide and dope it with tin, I can make a conductor, a heavily degenerately doped semiconductor. We're not going to do that. For a transistor, we don't want this. For our contacts, we want that. But in both cases, we want this band gap to be large, and you can compute that now, and oxides tend to have large band gaps here, and any states above that, you also want to have a large gap. So what are the implications of this picture? Can we use these for TFTs? And then I want to introduce one other historical twist. There was a man, a researcher, Bellingham in the UK, who for some years published work where he claimed he had made amorphous oxide conductors. And everyone said, oh, that's sort of weird. That doesn't really make a lot of sense. But Hideo Hosono at Tokyo Tech saw that there was something really interesting and unusual. And in fact, here's some that we grew just to show you. So if you grow these at low temperature, you can get amorphous oxides. So you might say, probably in 1950s, people said, why would you need to grow them at low temperature? Nobody ever thought, well, if you grow at low temperature, you can grow them on plastic. But you still, because of this S-state band, you still get good mobilities. You get as good mobilities from the amorphous material as from the crystalline material. That is extraordinary. And sometimes better, because you don't have grain boundaries in the amorphous material. A lot of them are quite flexible, as we'll see. Some very smooth surfaces. So in terms of electronics, if you want to contact different layers, you want smooth surfaces. These have all of those properties. Tunable optical transparency, they're essentially a glass, a semiconducting glass. And don't think of it as a random mixture of oxides and metals. In fact, we've done XFs and a lot of things, and the metals still have very definite preferred coordination numbers. Another way of looking at what's going on is here's silicon, and of course crystalline silicon has this nice, sp3 orbital sort of band structure. You start clipping the bonds by making it amorphous, and of course the conductivity and the mobility nosedive. On the other hand, with the oxides, here we have our S states, our S orbitals that are going to be the electron carriers, and if we move them, sort of bend them around, as long as they're touching, we still have good mobility. All right, you're going to say, well, it's not really that simple. So this is from Hosono, a review article, Hosono work, and there's some states in the gap. Are they important? They're important for some things. For others, you can completely ignore them. For things like the lifetime of IGZO transistors, if exposed to heavy light influences, it can be a momentary problem. But we won't talk about that. I didn't want you to think, this is completely naive. So let's make a transistor. And this we did with my colleague Bob Chang. And so here's the gate, or here's the substrate. It can be glass or plastic. You grow ITO on it, and there are different ways to do that. We'll talk a little bit about that and then here's our SAN gate dielectric, a little protective layer, because we're going to put the amorphous zinc indium tin oxide down by pulse laser deposition. So that little protective layer is just to protect from the laser plume. And then we're going to change the composition of the ZDO, zinc indium. And A here means amorphous, and this is the source and drain. This is a transparent array of transparent transistors on glass. And you can see they're really quite transparent. How good is the performance? The mobility is 160 on SAN. I mean, that just blows amorphous silicon away. On silicon dioxide is the gate dielectric. it's about 20. So the sand makes a big difference. So very nice, what's called pinch off, nice, very low hysteresis, transparency, really impressive. Send this to a journal, high-profile journal. The editor comes back and says, sorry, we don't allow advertising in our figures. Okay, get it out. The student then came back with a picture of Andrew Jackson on the $20 bill, and the editor came back and said, we don't allow pictures of currency in our journal. So what to do? So then the student said, the same student said, I got a picture of a tree. And I figured, who could ever object to a tree? So it went into print, I won't tell you the journal, as a tree. And then the student says, well, you know, I was backpacking in Uganda. And that's a picture of, after it came out in print, of the Ugandan national tree. When you wonder whether it's copyrighted, we could still be in trouble. But in any case, the performance here is really good. And let's take it one step further. The problem, you might say, well, okay, Bob, your pulse laser deposition were great, but this isn't solution processing. This isn't solution processing at all. So how does solution process something like this? And your first thought is, there's a technology that probably some of you know called sol-gel processing, where you sort of hydrolyze an organic precursor. You take this sort of very thick, I shouldn't use the word goo, let's say sol, and spread it, and then you heat it to 4, 5, 600 degrees C to densify the lattice. And so that's good, but what plastic are you going to use for heating it? You can't do that. So we had the following idea. This is the work of Myung-gil Kim, who's now a professor in Korea. Just think about it simply. Here's the conventional energetics. You have to put in all of this energy to condense the lattice. But suppose in the ink, if you like, the salt gel, we have an oxidant and a reductant. So the question Myung-gil asked is whether it would sort of self-ignite. You're not going to see any flames or fires, but it generates a lot of heat. And you can see this is differential thermal analysis, and we're comparing the combustion. We call this combustion synthesis versus the sol gel. So look how this is sort of a very rapid exotherm at very low temperature, just enough to sort of get it self-propagating. Here's the TGA. You can see very clean mass loss. And here's some crude initial transistors. I'll show you more in a minute. And works quite well. But let's now put some finesse on. This is just showing, this is Myung-gil's bending. He's got metal contacts here, but he's bending the transistor. It's on, they're quite flexible. I'll show you some videos in a minute on. This is on aerolite plastic. So it's an aerial polyester. You can see very nice transfer plots and output plots. Mobility of about 8, quite respectable. But now let's really take this a step further. Let's add our sand gate dielectric, and let's inkjet print IGZO. And why do you want to print IGZO? Well, for example, the iPad mini retinal display uses IGZO transistors behind there. Actually, so I didn't realize how slow. So they're sputtered. The sputtering, as near as we can tell from what Samsung will tell us, it's not like 5 seconds and it's finished. It's like 60 minutes of sputtering. And after you sputter it, then you have to do all this wet etching. We think you can inkjet print it just as well. But just to show you, here's the silicon gate dioxide gate dielectric. Pretty poor mobility. The sand dielectric, the mobility is about 8 times higher. And you can see if I look at these transfer plots, the red is the sand dielectric. And look, this is the operating voltage range. And here's silicon dioxide. And here's the operating voltage range. So you really gain a lot. And this is IGZO. Now, then you say, but okay, that was a spin coating process. That's kind of slow and tedious. You can inkjet it. But here's a different approach. And this is the work of a couple students, but Wei Huang would be and Xinge you would be the two people. Could we take that spray combustion, that combustion process, and rather than spin coating, make it a spray process, a continuous process? So this is the idea, and just to remind people, the Microsoft Surface 4 has IGZO electronics for driving the display. So what is it, if you spray combustion, produce IGZO films, what are they like? What is their defect density like? What is the mobility and porosity like? This is by a couple of X-ray reflectivity and one other technique I'll show you in a second. They're quite comparable. So you can make IGZO quality films, magnetron sputtered IGZO films, by this very simple spray, which we just do in a fume hood. And this is, I don't think you want to look at all this data, but we used for the density, positron annihilation spectroscopy and X-ray reflectivity. Here's current voltage scans, looks quite good. Here's mobility made by sol gel, combustion spin coating, spray combustion, and sputtering. And you can see the red one, the spray combustion is almost where the sputtering is. You might say, hey, I really want to have bottom contact types devices. So in fact, you can grow sand on top of IGZO. So you can put IGZO on the patterned source and drains, a whole array of them, and then the sand grows right on anything that has a hydroxylated surface. So you can grow the sand and then put on the gold contact. Works very, very well. Now, this is sort of interesting. So Binghao Wang got the idea. We were sort of thinking if you could incorporate a polymer into these oxide films, maybe they would even be more flexible. And so he's using here polyvinyl phenol. You can see from the X-ray that curing at 250 C, the stuff is still quite amorphous. This is the theta 2 theta scan. The films are optically transparent. There's a leaf. I hope to goodness it's not a marijuana leaf. I don't know what the students used there. Mobility, as you bend the material, this is indium oxide, by the way. With just the indium oxide grown on plastic, it cracks. On the other hand, the material with PVP and the indium oxide is quite robust and flexible. And let's see, there's some mobility. Yeah, and the mobility is quite respectable. It's around 10. But let's go one step further. So that was polyvinyl phenol, and it works fine. But what we asked was, and this is Wei Huang who asked this, suppose we used a very electron-rich polymer. This is this polyethyleneamine, and I'm showing it here. This is sort of a cartoon, but something really remarkable happens. You add a little bit of this to the indium oxide, and the film, spin-coated combustion synthesis, and the mobility jumps up. And then it slowly goes down as you add more PEI. And indium oxide is not a good material for transistors. It has good mobility, but it's hard to turn off. It has high off currents. So what we're going to do here is see the effect of the PEI addition to these transistors. And what you see is, this is sort of a model that we came up with, and we've hit these films with everything from XAFs to pair distribution functions to XP, you name the technique. So what seems to be happening for very low levels of PEI, so it's been known for these metal oxides for a long time, you could dope them with another metal and change a lot of the properties. No one ever doped them with an organic before. And with an organic, that helps the flexibility. But it looks like a little bit of PEI helps amorphisize the material. It fills traps. No, I'm sorry, this is not wraps, but traps, which means that the off current actually goes down. And you add more, and it gets better, and then you add too much PEI, and you begin to not be able to fill deep traps. So pretty remarkable. I'll show you a video in a second, but let me show you one other thing that Bing Hao did. He said, well, we've got this great spray combustion process. Why not make the whole transistor, every bit of it? So it's going to be all oxide. Sorry, no organics in this slide. But he made the masks, and the whole transistor, an IGZO transistor, can be made step by step with this spray coating combustion. The mobility of the IGZO is about 30. Samsung told us 5 is fine for the mobility, at least for the current generation of the Galaxy and things like that. We're almost 30. It works really, really well. And Bing Hao is one of those people who does everything. So first of all, they're quite transparent. He's used, this is the alumina dielectric. This is the zirconia. This is really a Fabry-Perot effect, looking at the thicknesses of the different layers. But here with TEM and EDAX, you can see the structure is just what we claimed. It's not something else. And from the EDAX, you can see the indium layers, the gallium, the aluminum layers. You can see that the ITO gate is crystalline. The others are amorphous. So really pretty neat. This is, let's see if I can. So this is a bending test. It's these transistors on, okay, it's going to work. On plastic, on aerolite. So this is the transistor. The indium oxide is doped with a little PEI to reduce the off current, but also to make it a little more flexible. And so the yellow is due to the PDI. It's not as if, we've contaminated this. You want to see it again, or you see? I don't know. Alex is nodding his head. Then the big question is, can I play it again? Figure out how to play it again. All right, we'll try once more. I mean, it's nothing profound, but people are talking about flexible electronics. I mean, this has a mobility of about, I think about 15 or so, and it's quite flexible. We've done that hundreds and hundreds of times till we had to make that machine, because you can't convince a student to do that 1,000 times. It's not part of what they like to do. So, okay, so one or two things that I think are really interesting. So our fuel that we've used earlier, we used this acetylacetone as the fuel in the combustion synthesis. And so it's not really environmentally friendly. If you wanted to have a factory, you have to get rid of those fumes and everything. So Bing Hao, here's the test. How many students here know what rocket candy is? Does anybody know what rocket candy is? Well, he apparently, as a kid, probably much to the disapproval of his parents, was mixing sugar with potassium nitrate, and you can make little rockets. And so he had the idea, why not use carbohydrates as the fuel in the combustion synthesis? So therefore, you've really reduced the number of sort of environmentally unfriendly chemicals, and it works beautifully. And this is the mobility versus, it turns out to scale as the heat of combustion of the particular carbohydrate you're using. So that's combustion, that's rocket candy. Rocket science I've heard before, but not rocket candy. One more thing. So this is work with my colleagues Mark Hersom and Lincoln Lahan, and they're very interested in making very unusual heterojunctions. So let me show you what we're doing here. So here's a silicon wafer, and what we want to do is compare, we want to look at a purified single-wall carbon nanotube array film in contact heterojunction with IGZO. So P-type and N-type, and we have molybdenum, we have IGZO transistor and a carbon nanotube transistor, and we're going to compare these two behaviors to what goes through that junction. And so this is just a description of the lithography, and what you get is really quite extraordinary. So first, let's just look at the the output data, and what you can see is depending on the gate voltage, you can get almost any behavior you want. And I mean, in terms of linearity. But more important, if I look at the transfer plot, so the red is the IGZO by itself. That's here, across this junction. Here is the single-wall carbon nanotube by itself. But across this junction, you get an output that looks like this. And so it's an ambipolar transistor would be sort of the 180 degrees. So this is really, and a very bright student named Deep Joe Waller worked out the theory. You can understand why, but one of the most interesting things, we showed it to Mark Lundstrom, who's a very, very good theoretical electrical engineer, and he said to us, he said, you've got a keying circuit. And he said, you guys know what a keying circuit is? No. These are materials scientists, and I'm a sort of materials chemist. It turns out that every Bluetooth system, Wi-Fi system has keying circuits to handle the frequencies, and usually it's a number of silicon transistors. He said, one of these is going to replace like 8 or 10 silicon transistors. So just to show you there's some really unexpected, all right, let me go back. I didn't mean to do that yet. I was so afraid it wouldn't work, and now it's like I can't turn it off. So this is an example of discovery, and part of what makes research fun. The last is, so we have a startup company named Flexterra, and their idea is to make something like the iWatch. It talks to your cell phone and everything, but with a much larger display, which would be completely flexible. And this is a prototype. It's not the final one, and it's called the Wove. And the company changed its name from Polyera to Flexterra to emphasize how important flexible electronics were.
This isn't a trick. This screen is meant to be twisted, bent, even rolled up. Startup Polyera spent 10 years developing the new technology. The real breakthrough is what's behind the screen. How do you make the screens that you produce bend?
So what we do is we start with new electronic materials, and actually what you see beside
this came from my lab.
These electronic materials. But we can then actually use traditional fabrication processes to turn those into the building blocks of electronics. And so these are transistors, and they are highly flexible, also highly mechanically robust to things like impact.
It's not bending the screen that's the hard part. It's everything that's in the screen. That's what's hard to make bend.
It's all those layers of different materials, and some of the hardest materials are the electronically active materials to make bend.
The bendable display uses black and white.
I think you've had it enough. So let's some conclusions. So that's the prototype, and we're moving toward manufacture. The cost will be very low compared to an Apple Watch. So we started off with a goal of making printed, flexible, transparent, unconventional electronic circuitry. I mean, we asked some basic science, chemical science and material science questions, and what we learned is that now we know how to make printable materials for air-stable organic CMOS. We can make the inks. We learned a lot about engineering, molecularly engineering gate dielectrics. We learned a lot about how you can tune the properties of the transistor. We did a lot with hybrid organic, inorganic circuitry. And I mean, there are some people who say it's got to be all inorganic or it can't be any good. People who say it's going to be all organic or it can't be any good. But maybe, in fact, the winner is some hybrid. I mean, our body has both organic and inorganic parts. It works some of the time. But the other thing, subliminal, I really want to emphasize is how important theory, computation, simulation of materials at a whole bunch of length scales is going to be important in the future to designing new kinds of substances. And just as a side, you saw a little bit already, it's applicable to soft matter photovoltaics. By soft matter, I mean organic type. So here's the people who did it. I'm just sort of the spokesman. First of all, where's Northwestern? So we're the first suburb north of Chicago. Our campus is on the lake. You can see it's nice and green. And there's swimming in the lake. There's beaches here and windsurfing when it's windy. And here's the Chicago skyline, a very large, very culturally diverse, exciting city. These are students and postdocs from 5 faculty and 5 faculty members at Northwestern, or faculty members from 5 departments. We have collaborators all over the world. We've published papers with Alex, for example. And these are the agencies that funded the work and made it possible. And again, the ultimate acknowledgement goes to those young people there. He's now just started as a professor at National University of Singapore. He just started at the University of Pennsylvania. He's at Purdue University. He's at the University of Milano. And I can go on and on and on and on. He's at Intel. He's back in the UK. He's at Tsingtao University. He's at LG. He's at Bayer in Germany. He's at Intel. He's at Intel. He's at Intel. He's at Intel. No, he's at Dow. He's back in India. So a really wonderful group of. He's at University of California, Davis. He's at Intel. She's at Hexcel. Intel, Hexcel. He's going to be heading off to Intel. He founded his own company. So a really wonderful group of young people. So with that, thanks very much for the invitation. I'm looking forward to giving a lecture on Monday. I have an office if you want to stop by and chat. Let's see, my office is right next to the chemistry headquarters. And then Tuesday it will move to IAS, which is like 1 floor down. So if you want to, I think my email address, I can put my email address in. Probably it's better to email me before 30 of you show up at my office. So it's t-marks@northwestern, all one word, .edu. So thanks very much.
Yeah, thanks, Professor Marks, for the wonderful talk. And now is the talk is the floor is open for questions. Any questions from the audience? Yes, Trini.
So after watching your video, I think you might need flexible battery to power your flexibility.
You're right. You got just the one.
Yeah, I will come to you for discussion about that. But I have 2 questions. One is about flexibility. The other is about transparency.
Okay, just one thing to add, and that is that that particular one was done in cooperation with e-ink.
Okay.
So it's electrochromic. So you do need a battery, but it's like a Kindle. You charge your battery once a week or something like that. But no, you still need a battery. You're right.
Sure. And about transparency, your demonstration is like you put your device on the your logo or leaf that they are very close. But if you have a distance between your leaf and your device, you may have the heat problem.
You mean Fabry-Perot type effects?
Yeah, for TFT. That you can see that it's very transparent if you put it close to your leaf, say logo or something else. But if you take it up, that if there's a distance, you may have the haze problem. Any comments about that? A second one is about
the student. Okay. He just wanted he was just holding the array in front of a camera, and he just put a leaf underneath just to show you could get light through. Yeah, Polyera has a lot of IP on just those factors, and also you might say, well, if you have multi-layers where they're all 100% in contact, for flexing, that's going to be the most disadvantageous thing. So they have ways where, in fact, the contact between the layers is controlled and not 100%, and that helps with the flexibility.
Okay. Another thing is about flexibility. Actually, most of demonstration is about it's bendable, right? So is it possible, like, to make it very flexible, like a cloth, like it can be?
Well, we showed this type of
twist,
thing.
Right?
But whether you're going to be able to crumple it, crumple it all up and pull it out, or the stretchability. And as we talked about the other day, everyone says it's going to be stretchable. It's going to be. For a huge percentage of the products, it doesn't have to be stretchable. We've lived with Band-Aids, since the Band-Aid was invented. Obviously, for certain things, you do need stretchability, but maybe we're getting too carried away about stretchability. Not sure.
Sure.
Any other question? Yes, Jim?
Thanks for the wonderful talks. I just have one question. It looks like in your TFT materials, right, sometimes you will use organic materials, right? But the substrate or some other things, maybe TFT, PD or something inorganic thing. So how about adhesion of your devices? Sometimes, you know, they will ready too many times, maybe they will
Start to delaminate. A couple things, yeah. I mean, so you design the chemistry so that you get good adhesion. Yeah. And so, for example, the sand gate dielectric, if say the gate has aluminum, which has an oxide coating, boy, it grows beautifully on that, or the IGZO, or things like that, or any metal that has an oxide coating, that's no problem. So we worry about things like that. In terms of delamination, you're right. So what you probably don't want to have is layers that each one is 100% contact, but you want to have maybe 10% contact. Very particular patterns that mechanical engineers have worked out to do that. It's a really interesting field.
Okay, so far we all have the question from the CTU, right? So how about we have from Hong Kong U and also later on WhatsApp, Poly U, okay.
But also we should announce where the Monday's lecture is. It's not here.
So
where is Monday's lecture? Yeah. Yeah, I don't want, if everybody shows up here, they're going to be disappointed.
So when Chongqing is looking.
Will be at B6605, the conference room of the College of Science and Engineering.
And it's 2 p.m., is it, or 3 p.m.?
2:30.
2:30.
Yeah.
2:30. Thank you, Eric.
3:45.
Okay, 2:30 Monday afternoon, right? And at the CTU CSE conference room, okay? Yeah, so Wallace, any question?
Regarding the oxide-based devices, you mainly demonstrate the for transistor application. Would it be possible for some which is related to light absorption or light emission devices? Oxide-based.
Sure. So there are lots of smart windows. Well, depends. So there's lots of smart windows that are designed, and probably some of these would to absorb infrared, so to keep a building cool. And what that really means is the plasmon resonance is way out in the near IR. So that's one. Another is electrochromics. So lots of oxides are used for electrochromics, and like in the 787, where the window goes dark or light. So I'm pretty sure that's an oxide electrochromic. Does anybody know, actually?
I think that tungsten oxide.
Right. Right. That's the classic one.
Yeah. So Gun from Poly U, right? Representative from Poly U.
Have competition between the
so,
local universities.
So
Yeah.
Who asked the best question?
Okay. Professor Marx, it's a great opportunity to see you again. Last time, actually, I think I see you is in UCLA. Last time you visited UCLA Yang Yang's lab.
Well, you may remember I visited twice.
Yes.
Because the first day was that shooting, that terrible shooting.
Exactly. That's in my small, tiny
they
office.
canceled my
there.
lecture.
Yeah. Yes.
And I was sort of in a room, and my wife calls and says, "Did you hear what's happening at UCLA?" And someone's been shot in Engineering Building 5, and where are you? Engineering Building 4. And so we're supposed to pull the curtains, the windows down, lock the doors, and just wait for the all clear. But unfortunately, I came back. And the second time, it was not so exciting, but I got to do my
yeah, that time is the first date of the shooting day. Sorry for that. Yeah. Well, okay. Go back to questions. We talk about in transistors, particularly in organic transistors. There has one of the major things there is a threshold voltage shift. That's one thing that has
with bias stress.
Yes.
So we understand that pretty well. And you can engineer the molecules to avoid a lot. What it means is if you put a lot of voltage on, chemistry starts. I mean, you're really starting to do chemistry on the semiconductor or the interface with the gate dielectric. And so we routinely test for that, and FlexTerra tests for that. And we've learned a lot about, it has a lot to do with HOMOs and LUMOs and things like that. Yeah, but that's obviously a concern. It's a concern. It's a concern with IGZO that also, if you have it in a light-emitting device, it's being irradiated, and in fact, that affects the threshold voltage of the IGZO. So what the manufacturers always do is put a little screen between the light source and the IGZO.
Oh, that's great.
And that's not so well understood, but it's probably different defects.
Let me ask a mechanical question, okay? You have so many layers here, including oxide. You bend it. How much strain generate? Why this oxide didn't crack? Do you know why?
Oh, there are no grain boundaries. It's amorphous.
But the layer, the oxide layer,
and it's
right?
thin. And it's thin. For most of the transistors, 50 nanometers thickness will give you enough current to light up an OLED or something like that. So they're quite thin.
Like the thing is very important. When the oxide is very thin, right? It can bend about 6-7% without cracking. Still all deformed in the elastic range.
Okay. So first of all, you're right. It's amorphous. And the other thing, the way the engineering is done, you don't have, for the layer under it or the layer above it, you don't have 100% contact. You only have certain places where it contacts. And that turns out to relieve some of the stress.
The key point didn't crack. You can calculate how much strain generated. Maybe it's 3-4% already before.
We've got I don't have the numbers with me, but we've got those numbers, yeah.
Yep.
Very stimulating talk. In your talk, you didn't mention packaging, but then you have two very interesting process. One is the sand, and the other is the combustion services of the inorganic. I just wonder, can you combine this process to make a multi-layer for packaging? Or have you tried this?
We're working right now on trying to make sand by combustion synthesis. There are a couple reasons to do it. I mean, if you sort of think about it, if you calculate the capacitance of something that's a multi-layer, 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over you actually gain more if you sort of mix them together and have the interface more diffuse in terms of capacitance. So we're working on that also.
Okay.
Good point. Yeah. I mean, all of these materials are going to be, the OLEDs, of course, are encapsulated, and those are probably more of an air problem and water problem than these materials, because we know that if you lower the LUMO and HOMO, you can protect yourself a lot and still get the band gap you want.
Okay. Thank you.
And you can use theory to predict things like where the HOMO and LUMO will be.
Okay, no.
Thank you, Professor Marx. I think the sand work is a very beautiful lateral extension of your pioneer research in nonlinear optics. And if you look at the structure, you have a beautiful alignment of a molecular dipole through the system of silicon oxide layers.
Yes.
Then have you ever thought about the multifunctionality? Because as a polar dielectric material, it would carry some like a piezoelectric property, pyroelectric property, plus light absorption and nonlinear optic properties.
Right. Okay. How should I answer that? Exactly. So first of all, Alex knows it began life as an NLO material, and you have very high second harmonic generation. The dipole thing, and whether you could make a nano piezoelectric, is something we'd love to have a collaborator to work with on that. But it's been, I think, the first of 2 papers has come out in chemistry materials. We learned to flip the dipole direction. And when you flip it, it's an engineer's dream, because they want to have the ability to move the threshold voltage to exactly where they want it. When you flip it, we showed you can move the threshold voltage of the transistor. Just flip the direction of the dipole. So you asked a really good question.
So you flip the dipole, just put in a different chemical function group, the function is different.
Exactly,
right?
and do the self-assembly.
Okay, any other question? I think so, maybe I can make it as one comment, right? Like, you know, if you look at this wonderful achievement Professor Mark has, right, and the recipe for his success, okay, I think in addition to his very diligent work and the genius thoughts, right, and you know, but then if you look at that, he has wonderful students, right? That's your recipe of success, and also he has wonderful collaborators, right? Okay.
And an understanding wife.
And also understanding wife, okay, right? Oh, so I should put that maybe right there. Yeah. So this is one thing I really also would like to promote, either in CTU and also in Hong Kong, right? Because, you know, we are always used to just fight individually, right? Okay, because you know, our system always looking for some of the individual contributions, things like that. But then if you look at, for you know, a lot of Professor Mark's wonderful papers in there, always have a multiple author, you know, the corresponding authors, right? You have Mark Hansen, Mariner, you know, all the different guys really contribute to really promote a wonderful science.
Make it a win-win situation.
Yeah, so I hope, right, this will be our culture, okay? You know, the PI can work together, but also students can, you know, work together, you know, to really build up this interdisciplinary
and teach
research.
each other.
Yeah.
It's wonderful things happen when students of different disciplines get together and collaborate and teach each other. Sometimes it's more successful when the faculty try to organize it.
Yeah, so with that, you know, let's please join me to thank the Professor Marks again, okay, for a wonderful presentation.
Thank you very much.